All right. So your project, it was a MATLAB, right? MATLAB project. You turned in early this week. So now we're ready to talk about your design project. I haven't got the write-up completely finished yet. I need to correspond with Dr. Zahid about that. But I'm going to give you an overview of what to expect, and then the specifics will be in that document, which I should have ready by Monday. So this is one thing that I need to make sure and double check with him, but I'm pretty sure it's going to be groups of 3, just like your other project. You're going to be designing an LNA. And so this is going to include theoretical design, simulation, and any sort of refactoring you have to do after you do your simulation, if you find that you're not meeting criteria or stuff like that. So I'm going to break this into kind of 2 separate, well, I guess 3 separate things. The first thing that you're going to have to do is basically, let's see, how do I want to write this down? So you're going to be designing an LNA that's going to go into a larger system. And in order to close the link, you're going to have to, achieve a certain gain and a certain noise factor. So I'm going to give you the specs of the other parts in the receiver chain, and then you're going to have to extract or basically figure out what gain and noise figure you need to get. That part's not too hard. I mean, there's some details in there that get a little tricky, but I think you guys have done most of those pieces already. So you'll get, from that you'll get gain and noise figure to close the length. And the system includes the encoding scheme. So in order to close the link for a specific encoding scheme, you have to have, encoding scheme and bit error rate. So in order to close the length with a given bit error rate, you have to get a certain gain for whichever encoding scheme you use, like for minimum phase shift keying or quadrift phase shift keying. There's a required output signal to noise ratio, basically. So you're going to basically be combining a lot of stuff that you learned from the first part of the course to get these 2 numbers, gain and noise figure. Other specs will be given, and those are going to come in the form of, say, your voltage standing wave ratios. What else do we have? Power consumption. Basically, well, I'll put these IIP3. What's the other one? Oh, the 1 dB compression. So these will be given. These ones you have to extract. And then from there, you can actually start designing. And at first, your design is going to go So what I mean by this is, if you're looking in terms of the input-output of a system, it'll look like this. You have, if this is your LNA that you're designing, you'll have an input and output, and they'll need to be matched to a 50 ohm. Input and a 50 ohm output. So you'll get your specs and design this thing, and this should be fairly straightforward, hopefully. The 50 ohm requirement just makes the matching simpler for now. So that's going to be basically stage one of your design process. And so you'll get, whatever gain, noise figure, etc. from that. Then in the second, I guess, stage of design, you're going to have to cope with some parasitics. And what I'd like to do on this stage is actually have you try to get as much gain as you can out of a system that has now been basically fudged by outside factors, without feeling any pressure to get these ones anyway. So obviously the higher the better. So I'm thinking that I'm going to award points based on, the group that gets the highest I'll give the most points to, etc. It'll be a small amount of points, like maybe 5 to 10 points I'll award for that kind of competitive. Let me put this in here. Competitive. And this is one of the things that I need to talk to the professor about is whether he's okay with that. It's just an idea to kind of motivate you guys to compete a little bit, but not too much. So it's not going to be a lot of points. It'll be some points. But what this one's going to look like is you'll have your 50 ohm input, and then you'll have some sort of parasitic network here. It will consist of some inductors and capacitors, basically to, I don't want to say simulate, but to give you something to work with that you might find in an actual system where you have like a long link between different parts of the system. And then out here you might have another parasitic network going into another 50 ohm input. So that's kind of the three parts as I see it. And then of course I'll put in some extra credit. I haven't really decided what I'm going to do for the extra credit. Usually there are 2 or 3 different things for the extra credit. I think I want to do something a little bit harder for extra credit than I've done in the past. But we'll see what the professor says about that, basically. Basically, I'm considering asking you to incorporate a mixing function into your LNA to see if you can get that to work. And if we do that, there won't be any necessarily requirements on the mixer as far as gain or loss, except for that I guess there will be a minimum or maximum loss that I would accept, like maybe 6 decibels or something like that. But it's mostly to get some experience with a more complicated system, and then doing some of the other simulations that the mixers require that the LNAs don't. Because I'll show you in a minute the set of simulations that you have to do to verify the LNA are pretty simple, and they don't take too much thought after you have the instructions. There's what I'm looking for. Remember, I need this so I can actually show you guys that. So, this is 2 or 3 items, and they're usually worth anywhere from 5 to 25 points extra. And I graded the whole thing out of 100 points, so this can be quite a bit. But when you get into the extra credit, you have to actually kind of work a little bit harder than the other part, I think, because it's extra, right? So in order to be extra, you have to put in more effort, I think. So I kind of grade the extra credit a little bit harder than I do the rest of the things. So if you try them, you will probably get some points, but it's doubtful that anybody will get all the points on the extra credit. So that's basically the project. There are a couple of other elements to it, but they're not too rough. I do ask you to do an area, a size estimate for the design, and that includes laying out capacitors and resistors, and also getting enough isolation between your transistors so that they're not talking to each other all the time. And then, of course, there's a write-up, and I provide you a specific format for the write-up, so follow that format. Other than that, I don't think that there's anything that I want to tell you that you won't find out better in the actual write-up itself. Do you have any questions about that?
The extra credit we have to do LNA with mixture.
Say it again.
For the extra credit, we have to do LNA like with a mixture.
For that part, for the LNA mixer extra credit that I'm considering, it would just have to be some mixing function going into, coming out of the LNA. So basically, it would be a frequency down conversion because you're in the receiver, and it would just be, you would have to show that it actually does the down conversion, and to do that you have to do the simulations that are outlined in the. There'll be another document. It's really kind of amazing. You have to do probably 2 or 3 times as much simulation to verify the mixer as you do to verify the LNA. So it won't be easy necessarily, and I will expect you to kind of pick up the slack between what I provide you and what you know more to do that part, if that makes sense. But yeah, it would just be some mixing function. So you could do like a diode mixer if you wanted to, or I guess if you could get it to work, you could just do like a passive, mixer. But it's one of those things where I really kind of wanted to assign a mixer, but I wanted to assign a single-ended mixer. And doing a single-ended mixer, there's a lot less, a single-ended active mixer, there's a lot less information out there about doing that. And so in order to do a double-ended mixer, we have to go into the idea of designing a balun and all that kind of stuff. And I kind of want to stay away from all of that and get a project that is maybe a little bit simpler, because not only do you have to worry about doing the project, you have to worry about doing the simulations and all that kind of stuff, and basically make your and my life a little bit easier, but at the same time provide people who want to try to do a mixer the opportunity to do that. So, oh yeah, I guess I should mention this. I will provide you a test bench for both these cases, for this one and for this one. And basically what that consists of is everything aside from your LNA. So it'll consist of the parasitic network here, this parasitic network here, power and ground. And by the way, there can be parasitics on power and ground as well. But it's single-ended. So your inputs, you have a single input and a single output. So my recommendation is to do a single-ended mixer, LNA. there's always, one or two groups who really want to do a double-ended, double-ended mixer or a balanced one. And that's fine if you really want to do that, but that's kind of on your shoulders. Because in order to do that, you do have to design a balun for the frequencies that you're going to have, and then you have to recombine the signal at the output. So So before I go to the computer, I guess I'll discuss a couple of other things really quick. When you turn in your project, I will give you instructions on how to do this, but and hopefully a reminder, so long as I remember to put it actually in there. So when you turn it in, you're going to include all schematics. This is so that I can go ahead and verify, what you got, what you list in your write-up as your gain and all that kind of stuff. In the past, I have forgotten to mention this, so I'm going to mention it now, so that you know, and then put it in the write-up to remind you. Let me say this really quick first. Project Journal will include all schematics.
The time is 0 o'clock.
I will tell you how to do that. And so the final note that I want to make here is when you turn in your write-up, when you turn in your write-up, the only acceptable format is PDF. If you give me a doc or a docx, I won't even grade it. And the reason why is because if you're like at a job and you're making a proposal or something like that, and you give them a document, first of all, it looks unprofessional. Second of all, those formats are totally dependent on the interpreter. And by that I mean, if you open a Word document, a Microsoft Word document on a PC, it will look different than when you open that same document on a Mac. And I don't use either, so what you send me will look completely different from what you expect it to be. The only way that you can guarantee that what you want me to see, I will see, is if you turn it in PDF format. So yeah, make sure that when you send me the final version, there's at least a copy in there that's a PDF. I guess I don't really care if you when you send, because I'll have you basically zip all this stuff up. If there's a version in there that's a Word document, make sure that there's a PDF in there so that I can actually see it, because I reminded myself of this when I was doing part of the setup for today. I had a student who had sent me a docx, and there's a table here and a table here in the other column, and then right here hiding behind the table there was an image that I couldn't even see. And that just has to do with the fact that I'm not using the same program to open the file as you guys did to create it, so there's no guarantee that what I see will be what you want me to see. And this doesn't just happen with images, this also happens with like mathematical equations and all that kind of stuff. So if if you've ever seen one of those kind of documents that kind of get mangled by the interpreter, that's what I want to avoid, basically. Okay, that's my rant on that. People normally do pretty well on the project, in spite of the project usually being kind of hard. And the reason for that is I want you to try something that's difficult, but I don't want you to be afraid to fail, basically. So when it comes to the, getting these specs out, if you're like, oh man, that's going to be really hard to get, well, it's probably supposed to be hard to get, but I also don't want you to be intimidated by it. So don't be intimidated by it, just go for it and do your best, and don't worry less about the grade. What? Stop telling me this. Sorry, I was talking to the computer. Worry less about the grade and more about the experience of doing the design, that kind of stuff. All right, so if I can, I'd like to switch to the computer operator. What am I trying to do here? So what I'm going to do now is I'm going to go ahead and walk you through the simulations that you'll have to do in order to complete the LNA part. And there's a document that I have that describes how to do all of these to you. And I will, of course, post it when I post the write-up for the project. But I wanted to at least have run through these once with you guys so that you've seen it, and so that I can talk just a little bit about some of them here. Oh no. They made me change my password. I'm not very good at this one. There we go. All right, so I'm just connecting to the Viterbi system. And then, as the instructions say, I change the CDS directory and start up Virtuoso. So it's really fortunate that it doesn't take a lot to actually lay something out in Virtuoso. I did this, what I'm about to show you today, and it only took me, the actual setup only took me about 20 or 30 minutes to design, to put these two circuits in. And so this is an example of a test bench. And so what it consists of is the input port right here. This part right here would be a parasitic network. I have parasitics on the ground and the power as well. So that's something that you'll have to deal with. If you're designing a circuit that has source degeneration, this will be part of your source degeneration network. And this is part of your, this would be considered part of your, I can't think what that's called, the pull-up, I can't remember what it's called, the pull-up network, I guess. I'll call it for now since I can't remember the word. And then for this particular one, I didn't have any parasitics on the output. I may for yours, depending on what I decide, and then here's the output port. So the part that you're designing is going to be this LNA right here. I'll go ahead and show you this one since it doesn't work anyway. It doesn't work in the sense that it doesn't provide the gain that we want. But just to remind you what this might look like as far as the pins and stuff like that. Can you see that on the screen? Is that very visible? I mean, okay. What I'll do is maximize it and then zoom in, and I'll just move around. Ow. So it's got the VDD coming from the external circuit. Oh, it's got, what this is right here is an inductor with a resistance in series with it to simulate basically an imperfect inductor. I will talk to you guys about that probably next week when we talk about the write-up that I've given you, and I'll tell you exactly what this means and how to calculate this resistance based on this inductor. value that you want. So this is a little tank circuit, and then he's got a cascode of transistors, and then he's got some source degeneration down here, and again, the imperfect inductor, same thing right here. This right here is a biasing network, and then on the input here and the output here, he's got these capacitors, and these are DC blocking capacitors. So basically what these capacitors are designed to do is let the AC signal in. So since the voltage across the capacitor can't change instantaneously, a high enough frequency signal coming from the input will be superimposed onto this DC voltage right here. Okay, and the same thing here. This is basically just to isolate this circuit from what comes before and what comes after it. You will need to do that for yours. I don't think I mentioned this, but it's fairly obvious. You got the input here and the output here. And then, of course, VSS, which is just the low voltage. It's basically supposed to be the ground for this particular circuit. One thing I do want to mention is that a lot of times you'll have very large transistors here. It's probably really difficult to read, so I will zoom in here. Nope, I guess not. Zoom in, zoom in. There we go. One more. So these two cascoded transistors, this one's, it's 300 microns by 200 nanometers. So that's a humongous aspect ratio. It's basically what, 600,000 or something like that? No, 6,000. Not 6,000. 1,500, sorry. Right, 1,500? 2 times 1,500 is, I'm sorry, 0.2 times 1,500 is 300, right? Yeah. 0.2, no. Why can't I do this? Yeah, that's right, I think. Anyway, it's a big aspect ratio. I'm gonna stop trying to do that math in my head. Maybe this is why it's not working. Microns. This one's 20 microns by 200 nanometers. And so that's basically that entire circuit. I just wanted to basically mention that there's biasing you have to do on your own, and also this isolation from the input and output that you have to do. Also, this right here combined with this, so this tank circuit and this capacitor basically alter the input impedance to match this over here. So this is a 50 ohm in series with a 1 nanohenry inductor, which is in parallel with a 50 femtofarad capacitor. So all the matching and stuff like that has to be internal in your circuit. So when you get to that second part, you'll have to include the matching inside your circuit. Okay, let's go ahead and get onto simulation. So that's basically an overview. So remember, to start the simulator, you go to Launch, ADEL. And once you get into the simulator, there are 2 things that you have to do every time. You have to change the simulator. Let it think about it for a minute. And then you have to include those model libraries. Here we go, come on. Oh, interesting. Okay. So include the model libraries by selecting tsmc25.spice. Hit OK. Okay, and now you should be ready to actually start setting up your simulations. So to do that, you go to Analyses, Choose, and for the LNA, the main simulation that you're going to do is an S-parameter simulation. To do the simulation, You have to tell it where the ports are that you're interested in, since it decides not to automatically detect them for you. So when you come in here, you have to populate this box, and the way that you do that is you go select, and then you click on the port, and when it puts these circles on it, that means it's selected, and then you click on this one. So both these ports are selected, and you go back here and you see that this area is populated, like so. You're going to be interested in sweeping the frequency in order to verify your design, because you will have to provide the gain over a certain bandwidth. So I believe that this circuit is designed for 2.4 gigahertz. So I'm going to have a center at 2.4 gigahertz for this simulation. I could do this by telling it to go from 2.35 to 2.45 gigahertz. I feel like it's just easier to say my center is 2.4 gigahertz, and I want you to do a span of 100 megahertz around it. So that's what those two things mean. Now you want to do a noise simulation, so you want to select yes, undo noise, and then you have to select the ports. So this one asks specifically which one's the input and which one's the output, and that's because when you're doing noise, you have to know where the noise is coming from outside the circuit and where you're measuring it at the output. And it does not know, so you do have to tell it. So select the output, and I'm going to select the input and verify that they're populated. And so that's all there is to setting up this simulation. It's pretty simple. The computer handles everything else. So going back to this window, I have my S parameter simulation set up. It tells me I'm centering at 2.4 gigahertz, 100 megahertz center span. And that's all there is. It's ready to go. If I hit netlist and run, and cross our fingers that everything works. Hello. Of course it's going to do this. Okay. So it's, I'm looking at this thing and it says my LNA example has been modified since last extraction. Re-extract the design file, and it tells me how to do that file check and save. So that's basically since I altered that one value. Check and save, and then I'm going to go back to that window and verify that that's okay. So LNA example's all good, and test bench, okay. All right, let's try again. There we go. So that took almost no time at all. So that's the main simulation that you're going to do for this thing. Now, you've done the simulation. Now, of course, you want to see the results. And to do that, you go to the results menu and you go to direct plot, main form. And this gives you all the options that you have to plot. So if you want to find the gain of the system, you can use the S parameters dB20. S21 means the signal at port 2, which is the output, due to a signal at port 1. So if I look at that, there we go. So I'm getting 18.2 decibels at the low end and 16.45, something like that, at the high end. Actually, 16.48. So if you notice down in the left-hand corner, it tells you where you are as you move this thing along here. So this circuit actually works pretty well. Apparently fixing that biasing network fixed everything. So there's the gain. You can also get the gain by hitting the transducer gain option and just hitting plot on that. And that should give you the same results, hopefully. Or no. What's going on? Sorry, it's been kind of doing this to me. I don't know what the issue is. It will show the window and then blank it out. So yeah, there's the transducer gain. Other things you're going to be interested in here are obviously the noise figure. So if I plot that, or not. If it does this to you, just, I guess maybe I should have waited. See, it's thinking, but it's not doing much. I'm wondering if I'm losing connection. Okay, let's try again. There we go. So there's my noise figure, or noise factor. So it's important in this case to notice that it's in millidecibels. So 635 is actually 0.635 decibels. So that's pretty good for a noise figure. So the circuit's actually pretty well designed. And I will ask you also to make sure that your circuit is stable, and that basically is this KF. I don't know why it's doing this. It was behaving much better earlier. But this is why it's good that it doesn't actually take that long to simulate, because you end up kind of waiting to do this. See, I don't know what it's doing. It's just kind of sitting there. You end up waiting to do this kind of stuff. So it's good to have something else to do, I guess, while you're... Why are you doing this to me? It would only do this, of course, while I'm trying to show somebody this stuff, you know. All right. I guess it's thinking. Something to try when if this happens to you is there's two nodes, obviously. There's Viterbi-SCF1 and Viterbi-SCF2. If it's doing this to you and it's convenient, try switching to the other one, because it's possible that it's under heavy load from multiple people trying to use it. Okay, if this doesn't come up in a second, I'm just going to go on and show you the other simulation. The other simulation actually takes some setup, and that's why I want to actually get to it. But basically, you'll carry out all these simulations for the version without parasitics, and then you'll do it for the version with parasitics, and attempt to get as much gain as you can out of that version with parasitics. All right, what are we doing here? Let's knock it off. I just cannot get this thing to behave. Whoa. All right. So I actually tell you how to plot everything that you need to, or yeah, I mean, basically for that set of plots, it's just, you know, you click on what you want to plot and you hit the plot button. All right, so in order to examine the IIP3, you have to change the circuit a little bit. And basically it amounts to editing this port right here. And you have to give it some extra information in order to label these things. And I tell you exactly what to... I tell you what to call them. I don't tell you the what frequencies to put in here, because I think that you should be able to figure that out on your own. The amplitude is minus 30, because this frequency is going to depend on what frequency range you're interested in. And then we're going to do display small signal parameters. And the pack magnitude is going to be minus 30 dBm. Okay, so that sets up the circuit to do the simulation. And we're running at slow on time. I'll try and hurry and get through this. So I updated the circuit, so I should be able to check and save it and have it still work here. I'm going to disable the S parameter analysis. And now, in order to do this particular analysis, I go to Analyses, Choose. And then the ones that I'm interested in are PSS, which is periodic steady state. And I need to give it a beat frequency of 5 megs or something that makes more sense to you. The number of harmonics need to be 2. And this one you have to select something in here. I always choose moderate because it gives you a reasonable amount of accuracy while not taking forever. Okay, and so that's that one. It's enabled. The other one that I need to do in order to get the IIP3 is the pack analysis. It got this from the PSS, the beat frequency. So I'm going to do a single point, whoops, not 2.4 gigahertz. Maximum sideband 2, and that should be that. So I'll click OK, and it's going to give me a little bit of information about those two simulations, so they're outlined right here. So now I'm going to hit Run and hope that this one behaves nicely. There we go. So that simulation took a little bit longer, but still didn't take very long. So now to view the results, just like before, you're going to go to Results, Direct Plot, Main Form. So the 3 dB intercept points, I need to go to the pack analysis, IPM curves, populate minus 30 here. So it lists the harmonics that are available at the beat frequency that I've given. So I'm going to look at this particular harmonic relative to this one. So this is the third order harmonic, and this is the first order that you're selecting here. And let's see. Okay, so this one's different when you actually want to plot this. You're not going to hit OK, or there's no plot button here like there was on the other one. You're going to leave this window open, and you're going to go to the schematic and click the input port. And hope it works. So there you go. So this is my 3 dB line, my 1 dB line, and they, thank you. And they intercept right here at 23.67 dBm. So there's your IIP3. And I believe that's all. So we're just in time. So all of these, there's instructions on doing all of this stuff. Keep in mind when you're looking at the instructions that the boxes are populated in a specific way. Some of that information you're going to have to change, mostly the frequencies, because I purposely made them different from what you might want them to be. So you actually have to think about it. Otherwise, you're just following instructions without thinking, which is bad. But the amplitudes and the magnitudes for that last one shouldn't matter too much. You know, you can just use the values that are given. But I just want you to be aware that, you know, like I said in the instructions to do those simulations, I was doing a simulation for something at like 4.1 gigahertz, rather than like for this particular student they designed. This was a previous student's LNA, by the way. But I'm going to change the parasitics and all that kind of stuff. Basically change the thing so you shouldn't be able to just copy his by watching the tape in slow motion. But you saw he got a pretty good gain and a pretty good noise figure, so it is definitely possible to get you know, to meet the requirements that I'm going to set, which might at first seem intimidating. But With that, I don't have anything else to add unless, do you have a question? Do you have multiple questions? All right, that's all I've got. Look for that, the write-up to be posted on Monday, and I will send an email when I do post it so you guys can look at it right away. And as often happens, there may be some errors in it, so if you guys do find something that doesn't make sense, let me know as soon as you can, and I will fix it and post another version so that everybody's kind of on the same page with what they're supposed to be doing. Okay? That's it. Have a good weekend. Thanks.